Welcome to the Explainer. So, if you're a focused learner looking to completely conquer any rotational dynamics exam problem, you are in the exact right place. Today, we're going to lay out the ultimate game plan to take those super complex physics scenarios and, break them down into something you can easily master. Look, we've all been there. You turn the page on your exam and boom, there's a rigid body problem just staring back at you. Beams, cables, hinges, balancing weights. It's definitely enough to spike your stress levels. But here is the secret. It all basically boils down to a highly repeatable method. Once you have the playbook we're going to cover, balancing that 10-kilogram beam won't even make you break a sweat. Here is our roadmap for today. First, the core rotational concepts. Second, your 5-step exam playbook. Third, drill 1 on static equilibrium. Fourth, the conservation of angular momentum. And finally, drill 2 on spinning dynamics.
All right, moving right into part 1, the core rotational concepts.
Okay, let's dive into this. Our first absolutely crucial concept is torque, represented by the Greek letter tau. Torque is simply the product of a force and its perpendicular distance from the rotation axis. So, simply put, it's all about the turning or twisting tendency of a force. Oh, and you've got to remember this golden rule for your sign convention. If the force tends to turn the object in an anti-clockwise direction, that torque is positive.
Just think about applying a turning force with a wrench. The force from your hand multiplied by that perpendicular distance along the handle creates the torque that actually gives you that powerful clamping force. It's great because it takes all this abstract math and grounds it right in physical reality.
Next up is our second core concept, moment of inertia, denoted by a capital I. This is defined as the sum of the products of each particle's mass and the square of its distance from the rotation axis. Now, that's a mouthful, but the crucial takeaway is that it doesn't just depend on the total mass of the body, it relies heavily on the shape of the body, and very specifically, exactly where that rotation axis is positioned.
Okay, on to section 2, your 5-step exam playbook. Now, this is the exact procedure for solving any equilibrium problem methodically. Step 1, sketch a simple diagram just to conceptualize. Step 2, sketch a separate free body diagram for your forces. Step 3, choose your axes and build a table to organize your knowns and unknowns. Step 4, apply your equilibrium conditions. And finally, step 5, solve the equations. Honestly, if you stick to this script, the exam problem basically solves itself.
Let's put this into practice with section 3, drill 1. Static equilibrium.
So let's execute step 3 of our playbook. We're going to deliberately slow down here to organize the chaos into a nice, clear table. We know the beam's mass is 3.0 kilograms and its length is 110 centimeters. Our unknowns are the counterweight, we'll call it W1 at one end, and the force exerted on the beam at point O. Laying it out visually like this guarantees we won't miss a single variable. Moving right to step 4. For a rigid body to stay perfectly balanced in static equilibrium, 2 specific conditions have to be met. The vector sum of all forces acting on the rigid body must be exactly 0, and the vector sum of all torques must also be exactly 0. Basically, we need both translational and rotational equilibrium to keep this beam from moving at all. And here's our final challenge. We've got our pivot point, our distances, and our weights mapped out on our free body diagram. By setting the net torque around point O to 0, we isolate our unknown. So, what is the exact counterweight W1 needed to maintain that perfect balance? The answer is 29.4 newtons. See, by just plugging the values into our torque equation, where we balance the clockwise torque of the beam's center of gravity right against the anti-clockwise torque of W1, we arrive beautifully at the solution. Following those 5 steps flawlessly leads you right to the correct exam answer, without any of the stress. Moving on to section 4, the conservation of angular momentum. Now, the crucial point here is this totally vital principle. If the net external torque on a system is 0, the initial angular momentum is exactly equal to the final angular momentum. In plain terms, without an outside twist to speed things up or slow things down, a system's total rotational momentum remains completely constant, even if the parts inside the system are moving around. Which brings us to section 5, drill 2, spinning dynamics. Once again, we're relying on our trusty playbook and organizing the scenario into a table. Imagine we have a heavy 200-kilogram wooden disc.
It has a 3-meter radius, and it's spinning initially at 4.0 radians per second. Then, suddenly, a 50-kilogram sandbag, because, hey, physics problems just love dropping random heavy objects, drops right onto the edge of the disk. And the sandbag starts with 0 initial angular speed. This poses a really critical question for our dynamic system. What is the new angular speed after that massive sandbag hits the edge? I want you to think about how adding mass at the very edge of a rotating disk changes the total moment of inertia. What's that going to do to the overall speed? Well, using the conservation of angular momentum, the calculated speed actually drops to 2.67 radians per second. Because the external torque is 0, momentum has to be conserved. But since adding that sandbag right at the edge drastically increased the system's moment of inertia, the angular velocity is literally forced to decrease to compensate for it. It's a perfect balancing act. Now, let's see how this builds into the ultimate classic physics exam problem, the student on the rotating stool. Every physics exam loves to use this scenario because it brilliantly illustrates these invisible forces in action. This classic setup makes the conservation of angular momentum totally tangible. When the student has their arms outstretched with the dumbbells, their moment of inertia is high, so they spin at a certain slower speed. But when they pull those heavy weights inward, they instantly lower their moment of inertia. And because angular momentum must be conserved, the rotational speed absolutely spikes. All right, let's lay out the exact variables for your final challenge. The student and stool-based system has an inertia of 5.43. They are holding 2 dumbbells weighing 1.25 kilograms each at an initial distance of 0.759 meters. Their initial speed is 2.95 revolutions per second, and when they pull their arms in, it shoots up to 3.54 revolutions per second. So, I'm going to leave you with this final provocative thought. Knowing exactly how much the speed increased, and knowing that momentum is perfectly conserved, can you apply the 5-step playbook to calculate the exact new distance of those masses? Grab a pen, sketch out your simple diagram, set up your table of knowns, and prove to yourself that you have truly mastered rotational dynamics. Thanks so much for joining this explainer, and happy studying.